Welcome to our session on basics of photovoltaics. In this session, I'll try to cover the basic aspects of photovoltaics as far as in perspective of electrical engineering. Means there is no certain mechanical aspect how we can have a manufacturing of the dimensional values of solar panel, etc. So talking about the photovoltaics, ultimately it's not a new concept. The photovoltaic system are similar in nature but differ in details from each other. It is therefore necessary to have a general view of the system. Once the true nature of the system is understood, any other individual product design becomes a mere corollary. For example, a solar water pump and a solar lantern both have the input from the solar panel or an array of different power processed through a same tracker mechanism followed by a load, which is either a lamp or a pump. So if we can divide this photovoltaic system, we can use these photovoltaic modules either in grid-tied mode or in standalone mode. But if we can talk about the basic of photovoltaic system, so in ultimate case, it works on the basic principle of photons are converting into the light. So this principle is not new for us. So when light falls in a certain material, the material has a capability to generate the electrons. So electrons are going to be pumped up from the material itself, and if we connect the load, we will use these electrons into the consumable way in terms of DC power. So let's begin the thing. So the photovoltaic effect occurs when an electron in the valence band of the material, generally this material is semiconductor, usually silicon, and other materials are available for photovoltaics, is promoted into the conduction band due to the absorption of one sufficiently energetic photon, that is a quantum of electromagnetic radiation that has been incident to the material. In fact, that in the semiconducting materials, as for insulating materials, the valence electron cannot move freely, so it's a bound. So we need some external mean. In this case, there is a light. So it will push the electrons towards the load. So with comparing with the semiconducting material, the insulating materials, the energy gap between the valence band and the conduction band is small, so that the electron can move easily to the conduction band when they receive the energy from the outside. Such energy can be supplied by luminous radiation, that is the radiation of the sun. Hence this effect is known as the photovoltaic effect. If you can talk about the preliminary member of the photovoltaic module, it is nothing but the PV cell. So the physics of PV cell is very similar to the classical PN junction. So if you can talk about the PN junction, and if you can compare this PN junction with the PV cell, so one, you are going to supply the DC source of energy to the PN junction, followed by measurable value of the load resistance, because when the diode will turn on, the load is must. If you will not provide the load, it is behaving as a short circuit. So when the junction will absorb the light, in case of PV or photovoltaic cell or an array or a module, I will cover in upcoming slides how this array, cell, module, string, etc. and then it's turned into the large power plant. So when the junction absorbs the light, the energy of the absorbed photons is transferred to the electron-proton system of the material and creating the charge carriers separated at the junction. So the charge carriers may be electron ion pairs in the liquid electrolyte, electron hole pairs in solid semiconducting materials. So how it is closely related with p-n junction, because in p-n junction basically there is electron hole pairs in the recombination. So if you can talk about the semiconducting material, over here this material is used, and when the light or the ray of the photons is going to be bombarded naturally on the material, it has a characteristic to generate the DC power. Keep this thing in our mind that it's a DC power, and obviously we need inverters that is to be connected with the modules at the larger ratings, so we can harness the AC power from the PV, that is photovoltaic module, and inverter, and then the load. Now if we can talk about the cell, generally the typical cell has a rating of 3 watt and 0.5 volt DC. Usually it will deliver 6 to 7 ampere DC current. So if we talked about the generic photovoltaic cell, we are having when the electrons and holes are created, when the photon will be bombarded over here, so at the depletion region there will be accumulated negative charge in the n type and accumulation of the positive charge on the p type, and the electric field in the depletion region swipes a hole into p side and swipes the electron on n side. So there is a recombination takes place over here, and the photon energy will be due to photon energy and the energy will be developed at this band. So this is very small structure because it's a cell. So if we can talk about when one can join the p type of material with the n type of material, that we have also learned. So when we are talking about the joining of these two junction, there will be a case known as the Fermi level. So when the Fermi level becomes equal, as a result band will bends. So essentially, if the light has an energy bigger than this band gap energy, then the electrons will knocks off in the particular atom and makes it freely movable in the bulk material. As a result, the electron goes into the conduction band, leaves behind the hole, which is also free to move, that is in the valence band. Now, what was that concept? The concept is like this. If you have n type of material over here and p type of material over here, the Fermi level in case of p type of material is usually nearer to the valence band, and that too nearer to the conduction band for n type of material. Now when the light will strike, the band bends like this. As I covered over here, as the light will strike, the band will be bends, and in ultimate case we will get the electrical power if we connect the load externally across this cell. So this is the typical situation when there is no sunlight. At that time the Fermi level remains the same. As in as a whole for the cell, because this p and n type material is already available in the cell, but at that time the p type behaving as a obviously p type material, in that case the more holes will be flow on both the side, and over here more electron has to flow. But if you will add the sun, that is insolation over here, at that time the material has a characteristic to have a recombination due to the effect of this photons, and there is the conduction band and the valence band, and this band has been bends and our Fermi level will become equal. So the photovoltaic effect will be developed in the cell, and for PV junction, that is photovoltaic junction, and if the load is connected over here, a significant amount of power will flow from the material, that is from the PV cell to the load. Now this is what the bulk material. So we are having top and bottom contacts. From that we can connect this external load. The conventional current I is the opposite of the direction of the electrons. So actually plus to minus the current will flow, or we can say anode to cathode. So whenever we are talking about the recombination process, so current is usually flowing into the opposite direction compared to the flow of the electrons or the charge carriers. So this PV source can be drawn as the current source, not a voltage source. So this is what the typical structure of the cell. We are having the top contact with the N type of material, then we are having the PN junction, and then P type of material, and then base contact. When the light will fall, we can deliver external DC current to the load. So the charge carriers in the junction, which will create the potential gradient and get accelerated under the electric field, and it will circulating the current. So it is nothing but the equal Fermi level. But in the case of semiconductor, if you can talk about the Fermi level, they will be very large in case of insulator, marginally small in case of semiconductor, and this is overlapped in case of the conductor. So the origin of the PV potential is the difference in the chemical potential, and that is what so called as the Fermi level. When these two levels will equal, by falling the light onto this, then the power has been generated. So this is what to say. Now I'll try to make it with step by step. So over here we are having the P type of semiconducting material and N type of semiconducting material. This is our depletion region. The plus and minus is there. So when the light will fall in, so at that time there is accumulation of the charges, and the electrons are going to be pumped up. In ultimate case, we are getting the current, means power. Over here the load is connected over here, because this is the physics of generation only. This principle is known as the photovoltaic effect. Now this is very interesting, how we can say that this is a PN junction. So if we can talk about the PN junction, we are having the external circuit for the PN junction in this case, and the power will flow from external junction to the diode, provided that some load is connecting over here. Otherwise the switch will be short circuited, or you can say in series connected there is some physical resistance. So if we are having the power flow from the battery or external supply to the diode, at that time there will be a supply from anode to cathode, and that is for the forward characteristic. But if you can talk about the photovoltaics, the power flow will be reverse. So the direction of the current is opposite over here, and this is how the characteristic of the IV. So if you can change the axis only, our current goes negative, and this has been demonstrated. It's a flipping of the curve like this. As the flipping of the curve will be there. See, it flips. As it flips, we are having the IV curve in the first quadrant, and that is nothing but the generation. This quadrant is dissipation, so we have changed the quadrant. Why? Because the direction of the current is opposite. So that's why the general question can be shared by the students and other people, why it is like a flipping of the same, because it's a changing in the direction of the current only. So the first and foremost question is how the solar panels or solar collectors are oriented. Obviously, one of the common answer is in the direction of the sun. Partly this answer is correct, but this is also depending upon the location. So, if you can talk about two main seasons across the globe, summer and winter. Usually in India we are having a monsoon, but across the globe they are following two seasons, a winter and the summer. Talking about the Indian winter, the direction of the sun is like this. So it will be rise in the east and it will set in the west. So it is in this case, this path it will follow. However, in the case of summer, it will follow this path. My point is this, it will not go in this direction. So as we are in the northern hemisphere, our panels are oriented towards south facing, and this angle is usually angle of latitude of the particular location, meaning this sun will not go in this direction at any point of time. So it is always towards facing towards the south. In the case of southern hemisphere, where least amount of people are living, they are oriented their panel towards north. As we are in India, we can talk about the panels are oriented towards south because we are in the northern hemisphere. So the panels are oriented towards south and at an angle of latitude. So by and large, if you can start with June 21 and at 21st December, and similar cycle will repeat because in intermediate case we are having the 21st September, again 21st December, again 21st March, and again June 21. It completes the cycle because it is depending upon one angle known as delta, that is declination angle of the sun. So this is the final outcome of the discussion. So when the light will fall on the PV material, then we are getting the external current flow to the electric load, and hence the PV effect converts the photon energy into the voltage across this junction known as the PN junction. So ultimately it combines. Talking about the basic construction of the PV cell with performance enhancing features. So we can accommodate some glass covers, transparent adhesive, anti-reflection coating. Then we are having the N type of semiconducting material, P type of semiconducting material, electron hole pairs, and then the sunlight will fall on it and the current will flow from the photovoltaic module to the load, and ultimately we are having the back contact. From back contact we can take the terminals out from the PV panel and we can connect it with the external world. That is nothing but the load or lamp load or DC load in this case. So some basic PV material you can say other than IV and PV plots. So the first, at absolute zero temperature, silicon is a perfect insulator. There is no electrons free to roam around as there are in the metals. As the temperature increases, obviously it warms. So the more electrons there are to carry the current, so its conductivity increases with temperature. In contrast to the metals, where the conductivity decreases. So electrons have energy that must fit in the certain allowable band. At room temperature, only about 1 out of 10 raised to 10 electron in the silicon exists in the conduction band. So when the light will fall, then those electrons are excited with the range of visible light it will contribute in the formation of the electron hole pairs and ultimately the current. So if we can talk about the function of solar cell, this is how the charge carriers and current will flow in the direction. So with this GIF, I just want to establish the effect of photovoltaics. This is the function of solar cell. Now if you talk about the structure of the module, up to here we have discussed. Then from the back side we have a metal contact, a laminate film, back glass and the cable connector. Now I'll go step by step. The protection layer, usually made up of glass. Thin film modules are made of transparent glass cover or a plastic. The front contact, it has to be transparent to allow the light into the cell. So like thermal collectors, in photovoltaics we are having the uniform trapping of the heat. Absorption material, obviously silicon as a single layer in most of the modules, where the light is absorbed and converting it has a characteristic of the material to convert that light into the electricity. Then we have a metal back contact, a conducting material at the back to complete the electric circuitry. Then we have a laminate film. So a laminate ensures that the structure is waterproof and insulated from the heat. Then we are having the back glass. This layer made up of glass and aluminum or a plastic, it gives a protection on the back side of the module. And finally there are the connectors, which is fitted and wired with the connectors and cables. There are two things which is new in this discussion. The first thing is the EVA, that is ethylene vinyl acetate, used in the photovoltaic industry as an encapsulation of the material. For the crystalline silicon solar cells into the manufacturing of the PV module, and backsheet is the final protection on the back side of the PV module. So till this we are just talking about the cell. The number of cells usually are connected in series. So we'll get the module and number of modules of series and parallel connection. We will get the array. So if we can talk about the back side in detail, we'll go with the framing structure. Then we are having the weatherproof junction box. So we can take the terminal out from this module. Then we are having the rating of the module, that is the data sheet. You can say a partly data sheet. From that you will be able to know what is the voltage rating of the module, what is the open circuit voltage, MPP voltage or rated voltage, short circuit current, MPP current or rated current of the module at standard test condition, and how much voltage it should be withstand and in which tolerance band that is to be incorporated on the back side of the module. It might be with the name of the manufacturer. Then we are having the weather protection cover. It has been assumed that ideally the life is 30 years. It has been observed that for 20-25 years PV is working in sufficient well mannered. Then we are having the cell over here. Then we are having the high transmittivity cover. Then we are having the frame clearance and then outside electrical bus. Now how we can convert this cell into module into array? Over here the panel can be counted as a module only, but in module, in certain projects or in certain experiments we are having the module characterization or cell characterization. then we may use this limited amount of cell with the series and parallel combination will become a module. Then module or a panel, the number of panels are connected in this way of the assembly of the series connected modules. Then we are having the photovoltaic generator as array and the string. The string is very important word because we will usually using the string inverters. And then we are having the photovoltaic generator. Talking about the typical rating of the cell, it is of 3 watt and 0.5 volt DC. Then we are having the cell thickness. Thickness is much important because it's a bulk material. It is having 100 to 500 micrometer with a thickness of about 0.3 mm and the surface of 100 centimeter square to 225 centimeter square. I repeat, this is the rating of the cell. Talking about the module, number of cells are used for the experimental purpose. It is converting into module. You can have the different methods of mounting the panels. As we have talked about, it is ground mounted, so usually this might be angle of latitude, or you can vary with change in radiation. We are having the track racks. You have seen this thing about the street light. There might be a side pole also, usually in communication towers you have seen, and that might be a top of the pole also. So over here it might be a kind of solar light concept. The light is LED lamp is situated over here. So whenever the during daytime this top of the pole or track racks modules will charge the battery, and at night we will use that power as a light. If you can talk about the cell, module and array, now you can able to know that the cells are converting into module and modules are converting into array. This is one demonstration. I just want to give the cell, module, string and array. This is the structure of 60 cells module. This is a structure of 72 cells module. This white color lines are the DC bus. Symbolically, this is the symbol of PV panel or a module. Number of cells are in series to form the module. This is alternative symbol of the PV module, and this is the parallel combination of series connected modules. How we can have a technical meaning of it. Suppose one module will generate 60 watt of power, 60, at standard test condition, that is at 1000 watt per meter square and 25 degrees centigrade. You may see my other videos to understand this thing in detail. So at this case we are having the 60 watt each, so 120 watt. Likewise 2 more strings, total 3, so it will generate 360 watt of power, or 6 360 watt of power. But the voltage and current is depending upon the series and parallel connection of the modules, and it has been decided for the grid tied system with the connection of the inverter, or else it will be decided with the battery rating for standalone applications. I'll just talked about some data sheets of the specifications of the PV module as we have talked about. Talking about the technical parameters, it could be 250 watt. The tolerance band is plus or minus 3%. The open circuit voltage is 37.8. The short circuit current is 8.7 ampere. The maximum power voltage, that is VMPP, is 31.5. The maximum current is 7.94. The module efficiency is 15.3. If you can talk about single cell efficiency, 17.2. The fuse rating is almost double compared to the short circuit current. Terminal box and the system voltage, this is most important. We can connect this module that can withstand up to 1000 volt DC. This is the weight, this is the operating temperature range. This is minus 42 dash plus 85 degree centigrade. These are the various physical dimension of the panel, and this is what the IV, this is my IV and PV curve of this panel. And similarly, the current temperature coefficient, usually plus in this case. Voltage temperature is change in temperature will collapse the voltage, and this is the power temperature coefficient. For 90% output, 12 years. This is important. So up to 25 years, it might be 80%. So if 100 watt panel is there, it will generate 100 watt power when it is new. After 25 years, theoretically, it will generate 80 watt. And similar case, it could be happen after 12 years for 90% output. This is one more data sheet of 250 watt module in the similar case. See, minimum system voltage is 1000. We are having the multicrystalline silicon, which is best suited for Indian weather. We have some protection standard in cable cross section. Similarly, this company Vari, one of the leading manufacturers of the same. This is linear degradation of the warranty that has been reflected over here. This is the thermal characteristic. This is the IV curve, the change in radiation. This is similarly IV curve with the change in temperature. See, the voltage has been collapsed. Over here the current has been collapsed. These are some examples of the PV system. Usually what happens, the certain controllers are need to be incorporated as an interfacing medium between photovoltaics and the load. So if we don't want any controller, we can directly connect PV with the load. As a result, load has to operate as the environmental change in the radiation and temperature will be there. Say for example, small fan. You may recall our childhood days when we are using our small cap, and in the top of the cap we are having one fan. So if it is connected with the PV, with the change in radiation and temperature, the speed of the fan will vary. So it is not controllable. So if you can accommodate the controller and the battery, then the load, according to the load demand, the PV will generate the power. And if the load demand is excessive compared to the rating of the module, this controller turn on the switch on the storage medium, and the storage acts as a backup system with the backup storage and generator. Still there is some more load. Then if this 1 plus 2, it will both satisfy the load demand. If there is high load, or due to somehow during night time and the PV is not there, then generator has to be turned on. So there are lots of things. So generator acts as a backup. Obviously, at all the times, generator is not only the option. We are using the batteries also as a backup medium. Then we are having the grid connected system. We are having the PV string, PV inverter, or you can say a PV module, PV array, whatever you can say. It is connected with the inverter, and then through inverter and the transformer, the power has been supplied to the grid or utility with the constant voltage and constant frequency. So with this, in this session, I tried to cover about the basics of photovoltaics, how the cell has been behaving, how we can change the IV curve, what is the difference between PN junction and the photovoltaic cell, how we can convert that module from cell to module and module to array, array to string, what are the installations way, means how to install certain PV modules, what is the role of other balance of system. I would also tried to incorporate some data sheet to get the exact idea of the material. So with this, I am thankful to all of you. Thank you very much.